exploration and discovery of OSPF. With OSPF, the principle is that every node has a complete view of the entire network and then uses a shortest path algorithm to compute next hops. The shortest path algorithm is Dijkstra's because it's the most efficient in this setting. And Dijkstra's algorithm, I will explain it on an example. It has the magical property that it adds nodes one by one, but whenever the nodes are added to the shortest path tree that is being discovered, they are exactly in the final positions. So it's a greedy algorithm, which one. The simplest is to explain it on one example. So here is a simplified view of the network, of the toy network we had before. It's simplified. I've removed some of the nodes that were the shared medium Ethernets to make the story a bit simpler. So here is the data structure that Dijkstra uses. Dijkstra is rooted at one node. All nodes have the same topology database, but all nodes do not do the same computation because node A does the computation of shortest path from node A to everywhere. Node B does from node B to everywhere. So the shortest paths that are computed are from self. We are at node A. Dijkstra keeps state information, which is the estimated distance to those nodes. Here I've put only the nodes. In reality, we have all the network prefixes, but let's imagine there is only the nodes that correspond to network prefixes here. Then initially, the algorithm sets the value of self to be 0 and the value to the other nodes that are known from the topology database to be infinite. And the set of visited nodes is initially empty, and that's the initial conditions. In addition, there is some information that will be used for building the tree that I will explain in a second. Then Dijkstra's algorithm, which is explained here, does it. If we ignore the details here, it's a loop where there are as many steps as there are nodes in the network. At every step, you find the nodes that is not yet visited that minimizes the estimated distance to that node that was computed in the previous steps. And you add this to the visited nodes, and then you do a small computation to find by which way can you reach this node here. So when we start, the set of visited is empty. At first step, then we add node A, because that's the only one that has a finite distance. So the initial step is always the same. And once we have updated node A, we update the distances to all the neighbors of the nodes that we have added to the visited set. So here, the neighbors are B and C. This information is available from the topology database. Remember, this map is available in text form at node A. So we can know that from B, I have a direct link with a distance of 100, and C, a direct link with a distance of 10, and same for F. So B, C, F, I can estimate the best distance known so far to be the values that are shown here. For D, E, the distances are still infinite. In addition, I compute, for example, for C, I compute what is the best path I had from A to C. Here it's very simple. There's only one because I have visited C from node A only. So I add to the predecessors of C, A, which is indicated on this cartoon here by the red arrow. So the predecessor of B is A, the predecessor of F is A, and that is the state we have so far. Then we continue. We add as a second node the node that minimizes the estimated value. The estimated value are those. There are 10 and 10, so we need to add C or F. We need a tie-breaking rule, for example, based on the name of the nodes. We add C first. So we add C, and when we add C, we discover new nodes for which we're able to compute the distance. There is D that had an infinite distance before, and now I explore all the neighbors of C. I find D, which is now at a distance of 20 from C. C was at the distance 10, so the distance I obtained to D, if I go via C, is 30. So I mark 30 here. I also visit B, and I compare what I had. From B, I am at a distance 10. 110 is my estimate of B if I go via C. This is less good than what I had before, because for B, I had already state information 100. So this is less good. This is not kept. In particular, the red arrow remains as it was before. If we had had a shorter distance here, for example, if that had been not 100 but 50, then the best distance would have been B, so this would have been removed, and instead we would have put this arrow here. For C, similarly, we go from C to F. We have something that is larger than what we had before, so there is no change. The visited nodes are AC, and the predecessor values are given by the arrows here. At next step, then we will add the node that has the smallest value among all the non-visited ones, which is 10. So we will add, which is F with distance 10. So we add F, and we do the same game. Here we get a better distance for E. So E now has a value which is 20, 10 plus the value from F to E. The other values don't change because F was already, C is already visited, we don't consider it, and the only new neighbor is E here. So that's step 3. Step 4, what will happen at step 4? Which node will be visited? Oops. Oops. I close in a second. Closing. And of course, the answer is E, because it's the one that has the shortest value. So that's the easy part of the question. Let's look at what happens next then. When we add E, then we have to explore the neighbors of E who were not yet visited. So that's only D. So what happens when we explore D? We find a distance to D via E, which is 20 plus 10, 30, which is the same as before. If it's the same as before, we could, in some versions of shortest path, we could look for only one shortest path, but it's not what is typically done with OSPF. If there are multiple shortest paths, we're happy to have several of them. We keep them. So in OSPF, we keep different shortest paths. So in a case like this, the code will instruct us to keep both because we have equality. We are shorter with equality. So we have discovered a second shortest path to D, which means that we put a red arrow here. If we want to go to D, we can come from E or we can come from C here. Other than that, nothing else has changed. So the value of D remains the same. And then we add, at the following step, we add the only remaining nodes, that remains, which is B. Then we add D, which has no effect because D is not connected to anybody who was not visited. Then we add B, and at B, there's also nothing new added. So that's the end of the algorithm. And the theory of Dijkstra's algorithm says that if you do this, you do obtain exactly the shortest paths, and they are given by the arrows here. That's the final state of the algorithm. Of course, the goal of this is not to write a tree of shortest path, it's only to find the next hops, in fact, the next hops from A. So shortest path can be computed using these red arrows backwards. For example, if I am at D, remember we are at node A and we wonder, how do I go to D? Then I start at D, I revert the arrows, I see there are two paths, one that leads me to C, from C I go back to A. So that says that I have a first path that is via C, and I have another path, if I do the same exploration, that is then via F. So I have two possible next hops to go to D, C, and F. This is how we could do it. In reality, the code of Dijkstra's algorithm that is in OSPF, or versions of OSPF, does not have two passes like I'm saying here. First, we run Dijkstra, then we revert the arrows. It's also possible to embed the computation of the shortest path directly, of the next hop directly in the code, but presenting in this way makes the code way more complicated. So I prefer this presentation. At the end of the day, the routing table, the only thing that A will get from this is this routing table that says, for example, in order to go to D, we have next hop C or F, distance 30, and for the other nodes, we have all the next hops here. So that's the only thing we use in this version of OSPF out of the shortest path computation. In reality, of course, as I said, it's a bit more complicated. We have this complication with the shared medium Ethernet, one-to-many networks that need to be added. So they are added typically in the routing table. And we're not interested in how to go to a router, but how to go to a network. So if a network is connected to several routers, like N7, then it's a node in the shortest path computation, and we perform the shortest path computation on the graph that includes N7. If N3, as we said before, is connected to only one router, we remove it from the shortest path computation, and then we add it to the routing table at the end by saying, how do I go to N3? Well, I go to B first, and I add the cost in order to N3 is the same as in order to go to B. Well, the next hop is also B, and the distance is the distance to B plus the distance from B to N3. So this is how OSPF will try to optimize the computation. In practice here, my diagram is not very representative. There are much many stub networks than there are intermediate networks. I mean, a network typically is made to connect devices, and you have many networks at the edge, and many than inside the network. An interesting side effect of the computation that we have seen is that it allows multiple paths to exist from a source to a destination. That poses a number of questions. The first one is there could be an exponential number of paths. When we revert the red arrows, whenever there is a bifurcation, we have multiple possible paths. So there could be a large number of multiple paths. So typically, OSPF will not allow this and puts a small bound on the number of multiple paths that can be obtained here. So we will not necessarily explore all of them, but have a small subset of them. The second problem is what happens when we are at A. A has a packet to send to D, and then it says that D can be reached either via F or via C here. So what should router D do? Should it send the packets randomly to one of them, or should it decide once for all about one of the destinations? What would you do? What do you think you would like to do if you are designing the code of OSPF? I close the poll in a few seconds. And we see that the majority says A, which makes sense, but still has a problem. Remember TCP, right? If you send the packets randomly over two paths, then you will you might create some reordering of the packets, which is okay. The internet allows this, and TCP will take care of that by storing the out-of-order packets into the socket buffer and waiting until all the missing packets have been received to deliver them in order. However, this will decrease the performance of TCP. So it is possible to do this, but it's considered bad practice today. So we try, when we design something in the internet, to make sure that all packets that belong to the same TCP connection or quick connection, we will talk about that a bit later. So let's say to the same flow, all packets that belong to the same flow should be routed together, where a flow means source and destination ports and source and destination address here. So this is something that we want to do. So the correct answer is probably A and D at the same time. So this is called per flow load balancing. How can that be done in practice? Well, in practice, you will apply a hash function to the flow identifier, which is, for example, the combination of source and destination IP addresses and port numbers, if you have some that are available here. And if there are two possible next hops, then you hash this, and if your hash is a good hash function, the outcome of the hash function appears to be uniformly distributed between 0 and 1. So that can be used to draw with a probability 50% which path you use. So if you say, if the hash value is less than 0.5, I choose the first path. If it's larger than 0.5, I choose the second path. It will have the effect of drawing the probability correctly. Plus, because we don't use true probabilities, but a hash function, it has the effect that all packets of the same flow will lead to the same decision. We don't flip a coin when a packet comes. Instead, we apply a hash. Flipping a coin is done in the computer by using the random number generator, which is truly random or approximately random for every call. Here, it's not random at all, in the sense that the same M will always, the same flow ID will always give the same hash value, therefore the same decision. So this is what most routers do today. In the Linux routers that we have, that's one of the zillion of options. We need to make sure they are well set. So we have to apply some configuration to make sure this is implemented. But that's a powerful benefit of OSPF, that if there are multiple paths, it will use all of them, which has, if you compare to other techniques that use only the best path, it has obvious benefits in terms of using the capacity. Multiple paths are typically available for backup, but here we use them also for load sharing. Right. If we have multiple paths and they're in backup, then of course that means we need a way to discover when there is a failure and reroute around the failure. This is viewed by OSPF as a change to topology. Changes to topology occur typically when there are failures. And major failures are software problems. So when routers are rebooted, there are also links that crash because of physical destruction, for example, of a cable, or software problems in the software that is in the links, for example, the switches here. When a router sees a change in the state of a link, how does a router see a change in the state of a link? Well, because there is the hello protocol. The hello protocol is done by OSPF. Most routers also implement a link-based hello protocol, which is called, for example, BFD, bidirectional forwarding detection. That's a protocol that is not OSPF, but is part of the Ethernet. Whenever you set up a link between two systems, if the BFD protocol is available on your machines, it will send every 3 milliseconds, it will send a sort of ping packet. And after 3 packets not being received, then you declare that the link is down. That's a way to detect a failure indirectly. Sometimes you detect it directly. For example, if your Ethernet adapter is unplugged, or if the wire is broken, then your Ethernet adapter will sense that there is no power on the line, so it will sense immediately the failure. So sometimes the failures are immediately detected by the local system. But if the failure is a repeater somewhere in the middle of the path that is broken, then there is no direct sensing, and such BFD or hello protocol are required to see. So when a router sees a change, either a link is down or a link is down directly or indirectly through the BFD protocol, or also a neighbor A is connected to B and speaks OSPF with B, but B all of a sudden doesn't speak anymore because I have not received any hello message from B, then I declare that I've lost connection to B. So that's a change in the local link database here. Then whenever there is a change, this router sends an LSA to all the neighbors. Hopefully there are some neighbors that remain, otherwise the network is disconnected. If the network is not disconnected, it will flood new values with a new sequence number, and that supersedes the old values. Here is an example. Here I have a topology that's a ring, which is a simplest topology with redundancy. Assume the link between A and B fails here. So before the failure, I'm showing the link state database, which is this picture, which is the same, and the routing table. So the link state database is the same, but the routing tables are, of course, different from every router. For example, we see that C here sends a packet to B via A. So C chooses this path for whatever reason via A. No, sorry, it has two paths to A via A and via D. Two equal cost paths to E. Now, when the link fails here, assume, for example, this is detected first by A. B will probably detect it also via, but since this is, if it's detected by hello or BFD, those are asynchronous systems, and we don't know exactly when one detects it. A might detect it 1 or 2 milliseconds before B. So assume A detects it before, then it will update its link state database, rerun Dijkstra, and this is the view now that A has, and this is the routing table. So in order to go to B, now A thinks that it has to go via C. And for D, so far it was, no, sorry, A has not yet had time to recompute the full Dijkstra. It has simply updated all the things that were unavailable. So the next hop, which were B, is removed here from the topology data. Whoops. Did I say it right? No, B. No, here I'm assuming A has recomputed Dijkstra and has found another path to B. A sends this information to all the neighbors, which is only C. So C will receive it. But of course, all this takes time. It takes a very short amount of time. It's probably a fraction of a second. But during a fraction of a second, there's lots of packets that are on the way. So if here, for example, D has a packet to send to A, here we'll see that D might send some of the packets to A via C. And such packets, if between A and C, if C sends a packet to A, correct, to B, for example, via A, because the routing table of C says one of the valid routes is A, because C doesn't not yet know of the failure, this packet will be sent to A. But now A knows about the failure and sends the packet to B back to C. So we see here, there's a routing loop. Packets to B from C are sent to A, and packets to B from A are sent to C. So they will, if A has a packet to send to B, or if some systems connected to A send some traffic to B, it will be diverted to C, but they will come back to A, which causes a loop. What will happen when there's a loop? Packets will expire the TTLs, but so for some fraction of time, B will be unreachable, and probably this link here will be in bad shape also. It will be busy carrying a lot of traffic that will eventually die. So that's something that can happen. It can happen because the topology databases are inconsistent. If everybody has the same topology database, even if everyone computes their own shortest path tree, because the routing is shortest path, there can never be a loop, because the distance to destination always decreases along the transmission of packets if you have truly computed shortest path. But here, that's not the case. The next hop, the routing table, is based on an obsolete versions of the link state database, and that can cause loops. This is why we have the TTL, or the hop limit, in IP packets. It is because of the fact that we can have updates to the routing tables that are not synchronous here. Of course, C will receive this, will update its own state of affairs, topology database, rerun Dijkstra, compute new values, and the topology database update is also flooded. So in fact, the flooding will occur probably more quickly than the update here. So D will eventually receive it here. And eventually, B will also detect the loss, which will correct its own thing, send a new update to everybody, and will also receive the update from A. And eventually, when this is happening and no packet has been lost, we are back to a state where the new topology is discovered by everyone. So this is how it will react to losses, but we'll see that the reaction takes some time and is asynchronous. And during the reaction time, there might be loops, there might be unpleasant things that happen in the network. Now, in a large network, in the interconnection of the world, if you consider a path from here to California, there's probably always some fraction of network that for some non-negligible amount of time is in one of those transient situations here. Let's check your understanding with OSPF. When a router crashes, how do all routers in the area detect that the router has crashed? I have shown here a link failure. Here, it's a router crash. It's router B crashes, for example. How will all the routers in the area detect this crash? I close the poll in a second. Closing. And the vast majority says A, which is indeed what is going to happen in most cases. So it's only the immediate neighbors, the peers, the OSPF peers of the crash router that will sense that this peer is no longer working, and they will inform the rest of the network by flooding new LSAs. Here. The hello protocol will allow only the immediate neighbors. So B is an incorrect answer in the sense that a router that's several hops away from a crash router will not detect it by the hello protocol. It's not doing hello with every other router. It is doing hello only with the immediate neighbors. C is still possible. Remember that the LSAs are the timeout value. So if a router, say M, has crashed and the values of the LSA received from M is in the topology database timeout, then it means that M is dead. But that would be a very severe case. It's more like, because those timeout values are more for safety and are very large, it's more likely that you have been informed of the loss of the router by the other mechanisms. Of course, OSPF, like any routing protocol, is critical to the health of a network, so it should be secured. So it is secured by several mechanisms, which are essentially authentication and encryption. I'll show an example called type 3, which is the correct name we give for SPF v2. And SPF v3 uses a similar authentication, but using IPsec, that we'll discuss a bit more when we talk about tunnels a bit later. But the idea is that first, all routers that are on same link means on the same Ethernet network, if they are connected to an Ethernet LAN, or that are directly neighbors on a point-to-point link. So all routers that are on link must share some secret key. So password in the lab or some secret key is shared between all the routers, and this key is used to authenticate the OSPF message we have here by adding to the message, so we compute a cryptographic hash of the message, of the source address of this router, and of a cryptographic sequence number. The cryptographic sequence number is, in addition, is a different thing than the sequence number of the LSA itself. Remember, OSPF sends messages by saying, here is my new view of my local neighbors and my local directly attached networks. Whenever there's a new version of that, we put a new number to it. So this is how the flooding mechanism works. And this is how a node knows when it receives a new LSA that it's new and not a repetition of an old one. Also, it knows that if you have already received it, you don't need to repeat it. So that sequence number is inside the OSPF message. Here we have a crypto sequence number, which is different from this and is incremented whenever we resend the message. Remember that OSPF does not use TCP. So when a router sends an OSPF message to a neighboring router, we use the stop and go protocol. The neighboring router sends an acknowledgement using the OSPF protocol type here. If this acknowledgement doesn't come, then the message will be resent. And if it's resent, it will have a new crypto sequence number. The goal of this is to avoid replay attacks, where you could record a message and send it again. If you send it again, you will detect that it's a repetition of a message that was already sent here. So we hash all of this, and we obtain a digest, and the digest is verified by the receiving router. When you receive a message, you know the secret key, you know the IP source address, it's in the IP header. That's the message you have, and the crypto sequence number is in the security header as well. So you can verify that this message is correct. The crypto sequence number is in a huge space that has in particular a boot count saved on disk. So whenever a router crashes and restarts, it will not create the same cryptographic sequence number. So that until we're all dead and also all our descendants in that number of years, thus this number will never wrap around. We'll talk more about aspects of routing security when we talk about BGP. Right now, let's conclude the OSPF part with the true story about OSPF. What we have seen here is just OSPF for a small size network. But in fact, in larger networks, people have found that after all, link state is not such a good idea. Remember, we've seen distance vector. Distance vector has the benefits that we don't have a routing information base other than the routing table itself. So it's very compact. It's the most efficient way of doing routing. But it has a number of problems, in particular of convergence when there are disconnected parts and so on. So, but it has scalability benefits that OSPF does not have. So OSPF that has been around for 30 years has been very successful only in the past 15 years. Before that, the routers were simply not powerful enough. They didn't have enough disk and CPU to run OSPF over decent-sized networks. Now it's possible, but still, we can improve the scalability by introducing what is called areas. So with OSPF, in fact, the flooding that we do and the topology database, all that story is valid only inside an area. And an OSPF network of a large size typically has multiple areas. And it has a hierarchical structure at two levels, where one of the areas must be backbone. It's called area 0 in OSPF jargon. So here I'm showing a network that has three areas, area 0, area 1, and area 2. And why is the backbone area 0 called backbone? Because all traffic that goes from one area to the next, to another one, should go via the backbone area. This is how we avoid complexity in the area description. So the principles are, inside an area we do link state, and there are routers that must be at the boundary between areas. So they're called border routers, and a border router is, for example, X3. It belongs to area 0 and to another area, and it belongs to both. That's one way of designing interaction between areas. We'll see that in BGP, when we interconnect two OSPF domains, for example, we put a BGP router in the first domain and in the second domain, and they have to speak together. Here we save on routers by putting one router that's in the two areas. This is because in BGP, we are expected to work between different administrative domains, so we don't trust another domain enough to be able to share a router, right? Sharing the configuration and everything, you typically don't do this. Here, this is all inside one domain. Even if there are multiple areas, it is one domain. And now the trick is, how can that work? And the trick, we'll explain now, is based on injecting aggregated distance information into the local topology databases here. Let's see on an example here. Here, I'm zooming first on area 2, the right area here. So because we use the principle of link state in area 2, all 4 routers in this area know this map here that I put in gray. The 4 have a replicated view of this that they've acquired via flooding here. Therefore, all routers run Dijkstra, for example, and X4 can compute its cost to N1, which is 10, and to N2, which is 16, and X6 will do the same and will have the reverse value of the distances to those here. That's the story we've seen so far. Right. Now, routers X4 and X6 that belong also to area 0 will put into the topology database of area 0 the information that they have acquired for area 2, as if they would be directly connected. So X4 will say, I know about prefix N1 and the distance is 10, and I know about prefix N2 and my distance is 16, and will flood this information into area 0 using the LSA mechanism that we have seen so far. At the end of this flooding, the 6 routers in area 0 will have this map. So this map contains, of course, the topology of area 0, all the directly attached networks, plus the networks that are indirectly attached. I said that router X4 does as if it would be directly attached. It's not 100% exactly like this. Of course, there is somewhere a bit in the record. When X4 says the information, I am attached to N1, it says, and it's called an external network. It is not something in my area. But practically, it is exactly the same here, as if X4 had a direct link to those 2 networks, and this one also here. Now, the story continues. Inside area 0, all routers can compute their distance to those 2 prefixes, N1 and N2, by applying the usual formula that we use here. It is as if these would be stub networks, right? We can compute for example, X3 can compute the distance to X4 and add the distance to N1, and same to X6 and add the distance to N2. So this will give us this additional distance here. We don't use Dijkstra for that. We could add N1, N2, etc. to the graph of all of Dijkstra and rerun Dijkstra, but this will not be the most efficient way, because typically there's a huge number of the yellow prefixes. I mean, imagine you're an internet service provider. The yellow prefixes are perhaps the entire world here, or a large fraction of the world here. So this is typically a very large number. So what you do, typically you run Dijkstra here, and then every router, like X3 here, will now compute this formula separately of Dijkstra and in parallel by saying, in order to go to N1, I know N1 is attached to 2 routers. I compute the mean of the 2 paths that go via those 2 routers here. By the way, this is the same computation that is used in distance vector. This is called the Bellman-Ford formula. So X3 will do that, and will compute that its distance to N1 is 23, and its distance to N2 is 22. So now X3 has this information. When computing this, it will also remember what is the shortest path. For example, to N1, the mean of the 2 was via the border router X4. So when X3 wants to go to N1, it had 2 possibilities via X4, X6, and this one gave the mean. So I know also the shortest path should go via X4. So in my routing table, I will put that in order to go to N1, I have to go to whatever shortest path is the same as going to N4. So at the end of the day, X3 knows this information. It knows distance to N1 and N2. X5 has done the same thing independently and in parallel. And now X3 and X5 are also in area 1. So they inject into area 1 this information that they know how to reach N1 and N2, and here are the distances. And now all routers in area 1 will know this and will have this topology database here. Now, whenever the same thing will happen, when a router like A1, for example, needs to compute how to go towards N1, well, it knows that N1 is reached via X3 and X5. Through Dijkstra, I know what is the distance to X3 and to X5. I compare the 2, and I know what is the best. And for example, A1 finds that the distance is 33 and that the best path is via X3 here. So those are the optimizations that are done, and this is how it works with multiple areas. Quick question to check your understanding. When applying the Bellman-Ford formula to compute distance from self to N1, for example, done at A1 in area 1, how does A1 know the different values of those distances used in this comparison? I close the poll in a few seconds. Closing. Closing. And the majority says A, which is the correct answer, but a large minority says something else. So let's have a look. This is the vision that we have in area 1. That's the only vision we have. So all routers have this information here. So when A1 computes the distance to N1, the information of how to go to X3 comes from the routing table, the output of Dijkstra, but the distance from N1 from X3 to N1 is in the topology database, has been acquired through link state advertisement sent by X3 in this case here. Good, I skip this one and this one. Let me mention just that the use of OSPF that we've seen is limited to very basic stuff, which is computing the shortest path, which in the vast majority of cases is the only thing that is done. But there are many networks that do smarter things, like, for example, to do multi-class routing. Multi-class routing consists in having different types of traffic. For example, for internet telephony, we would like perhaps to compute paths for internet telephony that give priority to shorter delay rather than the shortest path in terms of number of hops. So we might, that may be the same. Typically, if there are fewer hops, the delay is less, but it's not always the same. You might have delays. You might have hops that are, for example, long distance at very high throughput that you want to use, but that have a large delay. And you might have other links that have shorter delay, but not large capacity that you want to reserve in some sense for internet telephony. So that, of course, is very easy to do once you have a topology database. So you can do the calculation that we have done for different classes of traffic. So we can have a class A that has given link state, given cost attributes, and class B that have another class attribute. For example, for class A, we could consider that the cost is equal to an estimate of the true delay on the link, not the cost, virtual cost that we give to reflect 1 over the capacity of the link. So that's an example that is used in many networks. Explicit routes is another example here, where explicit routes, which is a form of source routing, where an edge router can compute the entire path. Remember, we've talked about source routing as a possibility in ad hoc networks to simplify the intermediate routers. This can be used also in industrial applications, where an edge router computes the entire path using OSPF. You have a topology of the network, so we know the entire path from OSPF. In classical use, we just distill out of it the next hop, but we could compute the entire path. And if we have an application that requires source routing, that gives us the path that we can put in the header. This is done typically in what is called deterministic networks, where we want to have full control of the end-to-end latency. So we don't want, we want to know at the edge what is exactly the path we will take, because then we will compute the delay and see whether it's okay to have this delay. And let me conclude and steal 1 minute of the break with this last question. OSPF is routing protocol is layer 3, okay. But now if we don't want to be too religious and be a bit more pragmatic, we could use the same idea for a network of bridges. So if I have a large number of bridges here with lots of VLANs, like we have a TPFL, for example, and we would like to make a possibility to interconnect all those VLANs via something like OSPF here. Right? The problem, what is the problem? Well, the problem is I have, for example, at TPFL, we have 1,000 base stations. And whenever you join a base station in the morning, you're associated with the VLAN of these base stations. And then you move in the day. So your VLAN moves with you. And then we would like to interconnect all the VLANs together here. And if we do that with the form of bridging, of VLAN is layer 2 stuff here, we need, for example, to set up a spanning tree for the red VLAN, another one for the blue here. Can you imagine using link state routing for that? You know, it was the wrong. Okay, let's see what your imagination says. I close the poll. And there is a large variance, but many of you prefer A. Well, this is exactly what Cisco did here. B doesn't help because the MAC address don't say in which VLAN the machine is. So the problem is really to detect whether there is a need to have a VLAN attached to this router. So you can put this, you don't need to put the MAC address, but just a bit saying for this VLAN, it is present on this router. And then since you have the topology database, you can compute a spanning tree using the topology database, using Steiner algorithm, for example, or whatever algorithm for spanning trees, that will make sure you can have a tree that spans all the routers that have the red and the blue VLAN here. So this is exactly what is done. So there's a number of protocols. There's SPB protocol, and there's the Trill protocol. Those are two protocols that are used to carry MAC packets inside IP packets in order to extend VLANs here. So as we've seen with beer, that kind of ideas, we see that this is used a lot. So we'll talk more about tunnels in a later section. Good. Thank you for your patience. We do a break. And let's restart with a little quiz. Here's a network, the simplest of all redundant network, a triangle. Assume all nodes receive an input traffic lambda, and the links are 1 gigabit per second in every direction. What is the maximum value of lambda that is possible, assuming traffic is uniform in the sense that the traffic from A goes 50% to B and 50% to C? So the question is if we have OSPF routers, assuming the link costs are the same here, or if we use transparent bridges, if A, B, C are transparent bridges. What's your guess, or educated guess? I close the poll in a few seconds. Closing. And the majority says B, which is the correct answer. Well, here's a way to visualize the constraints that are happening. If we use OSPF, then the network will use all the paths. For example, to go to C will go this way, to go to A will go this way. So the blue traffic will be split into two, and the constraints are obtained by saying lambda over 2 is less than 1. Similarly, everywhere, so we have 6 constraints, and they're all of this form. So lambda is less than 2. If we want to maximize lambda, the answer is 2. If we use the spanning tree will break one of the links because it's not able to use a topology that has loops. So for example, if it breaks this here is what happens to the flow. All the traffic from B that goes to A and C goes first via A, so we have an intensity lambda here, and then half of it goes there. Similarly in the reverse direction. So if I look at the constraint, lambda is less than 1, lambda 2 plus lambda 2 is less than 1, etc. We find the constraint lambda is 1 gigabit per second. So the total throughput we can have for this homogeneous and symmetric network with OSPF is 2 gigabit per second. With spanning tree protocol is 1 gigabit per second. So you double the capacity by having OSPF software instead of a spanning tree, by having routers instead of bridges. You can keep bridges here, but if you do shortest path bridging using Trill, for example, like we discussed before, then you would have this performance here. So that's the interest of shortest path routing versus spanning tree. Let's conclude this section about something that's completely unrelated, but we need a home for this short section. So I put it into routing because it's an alternative to routing that is called software-defined networking. The terminology, like often is the most complicated part. It's not really a network that's defined by software. It is in reality something more basic that we will see, which is a centralized control of the routing decisions. But before going there, let's talk about something that is that in principle, IP routers, they adhere to the principle of IP, but since it's not a legal requirement, it's just if you want to be compliant with IETF rules, you do this. But in software, anybody can imagine other ways of doing it. So it is done. And in particular, many networks want more control. For good reasons, sometimes, for example, to handle mission-critical traffic with high priority. But this can be done in simple way by looking at the IP header priority field. It may be, for example, to handle denial of service attacks. Here, that's an example given in this paper of SIGCOMM a few years ago. You have a lot of red traffic that is being monitored. So in any network, you do the routing and all these things we see. You also put in place network monitoring tools that count how many packets are sent. So all routers typically collect this information, and then you collect it in a central computer. And you see, for example, there's a lot of red traffic, and much more than we usually see. So the artificial intelligence that does the monitoring will say the red traffic is suspicious. And one solution that is often done in a case like this is to have special routers that will analyze the red traffic more, or simply force the red traffic to go through a router that will slow it down. In some cases, in the past, we did a lot of deep packet inspection. What does deep packet inspection mean? Well, the shallow packet inspection is what we normally do with a packet, which consists in looking at the header. If you're a bridge, you look at the MAC header. If you're a router, you look at the IP header. If you're a NAT, you also look at the port number. That's the normal packet inspection. Deep packet inspection means you look at more things. For example, you look at the port number, and if the port number is 53, that's DNS, you may look at the text of DNS query, for example. So is this guy looking for information about Tibet, for example? Then if you're looking about a website that has a given keyword in it, you can look into it. That's called deep packet inspection. It's done for essentially countries that want to monitor everything that you do. It is defeated by end-to-end encryption. So if you use a VPN, or if you use, like we discussed, TLS, which is normally what you do if you go to HTTPS server, or if you use QUIC for anything, the content is encrypted, which is a good thing. That makes deep packet inspection not possible. But there is a middle term, a middle ground between the shallow packet inspection and the deep packet inspection that tries to gather all the information that can be gathered. For example, if we have an IP in MAC packet that itself contains a VPN tunnel that gives us some information also, that can be used for taking decisions about the packet. For example, the VPN traffic of the blue companies might be considered blue traffic that we don't want to do anything about it. And all the rest, we might let it go through some other part of the infrastructure that will mitigate at least the effect of the denial of service attack. Or if there is an established denial of service attack, if you're really being attacked, you may remove some of the traffic entirely by sending it to dev nodes somewhere. How is this done? Well, this is done by added to routers what is called per-flow forwarding rules. Per-flow forwarding rules, I'm giving an example here, is a data structure that exists in a router or in a bridge, by the way, so any packet processor, any packet processing machine, that comes in addition to what I often call the IP forwarding table, which is often also called the routing table. That's the normal thing you have in a router. You don't need anything else. But you can, and most routers have, in addition, the possibility to have what is called a flow table. The forwarding table is searched by using the rules of longest prefix match. The per-flow table are searched by priority field. So the rule in a flow table is when a packet comes, you try to find a match in the flow specification. If there are multiple matches, you look at the priorities. And hopefully, there cannot be multiple matches with the same priority. Otherwise, we don't know exactly what would be done. Assume we have those rules here. So we add to router R1 those two flow specifications and actions that says anything that comes with input 0, interface 0 here, destination b.d.anything, action is send it to output 2. So we see this is a routing decision. So this is superseding the routing table. The routing table acquired with OSPF might say something. Here you can, for a given flow, decide for something else. At your own risk, of course. You can create loops with flow tables. So there's considerable risk in doing that, but it's possible to do it. Another rule says anything that has destination b.d.star, you drop, you kill the packets. Of course, those two rules are overlapping. We see that the two rules apply to anything that has b.d, but the first one only if it comes from packet 0, from input 0, and the priority says that the higher priority should be applied first here. So, for example, if Lisa sends a packet to b.d.h2, which way will the packet come? And same thing for Homer, right? Given those rules. Closing the poll in a few seconds. And the correct answer, which is the majority answer, is E. Here, Lisa's packet is coming on port 0, so it matches this rule and this rule, but this has higher priority. So it is sent to output port number 2, where nothing special happens, so it will be delivered in this way here. Homer's packet is coming on output port 3, so it matches only the second rule, so it's dropped. Here, the flow table has precedence over the IP forwarding table, so you first do this before doing something else here. Imagine you do this in a data center or in the network of an enterprise. You want to set up the rules for a number of reasons. for example, as we said, for security or also for a number of purposes, of quality of service purposes. Then there's considerable complexity in doing it. So we can go into every router and configure the rules, but this is not a very efficient way. So the obvious way is to download the rules directly into the routers. And this is called exactly software-defined networking. So software-defined networking assumes that the routers or the switches are able to receive instructions to write this per flow table here. And these instructions come from a central controller. And the complete thing is called software-defined networking. The central controller speaks with a piece of software called the listener, the SDN listener, in every packet processing machine over a TCP connection. So the messages come here, for example. They might be switched or routed via multiple hops, but as TCP connections. So that's very different from a routing protocol where all the routers in between participate in the decision. Here, it comes directly from a central location to the final node here. This is software-defined network. Now, you could imagine that you replace OSPF by software-defined networking, right? We could say, after all, I can collect a topology of the network. I know the network, I built it. And then I can compute the routes in a central computer, which is probably more efficient than doing it in a local router processor, and then download the routing information and also per flow information if I need something. Would that be a good idea? I close the poll. Closing. So the answer seems obvious. It's a bad idea because in order to download the rules, we need to set up TCP connections. So we need the network to work, right? We need the routing tables to be working. So we need to bootstrap connectivity. And for this, if it's bridges, we need the spanning tree protocol and the learning mechanism of bridges. If it's routers, we need OSPF or another routing protocol. Only once we have that, we can speak to the routers. That seems obvious, but Facebook did not follow this rule. So last year, there was a major Facebook outage where some of the data centers and also the DNS networking infrastructure of Facebook was unreachable. And they did not use, they used SDN for everything, including for superseding the routing tables values. Which means that when everything went wrong, they had no way to talk to the routers because the routers didn't work at all, right? So this common sense should be followed. Voila, that's the end of our discussion of routing protocol, at least inside the domain, which is exemplified by OSPF, and also, to a large extent, by SDN. But we will not do labs with the, well, there is a lab question on SDN in lab 4, for those of you who will be taking the option. That's the end of this module. Any questions on this? In the internet, in the global internet, what is this figure illustrating? Well, it's chaos. It's an intersection in Paris. So there's priority to the right, and plus it's Parisian, so they don't really follow. You see cars that are trying to find their way, but they're blocked by other cars who themselves are blocking other cars. So everybody is blocking everyone. That's an example of congestion collapse. The throughput of this intersection is quasi-zero at the peak hour. That's a symptom that there's a lot of traffic, and because there's too much traffic, the throughput decreases. The capacity of the intersection is reduced exactly when there is too much traffic. That is congestion collapse. That has happened in the internet in '86, and we'll see what the problem is. So in '86, the internet, which was working at those fantastic bit rates, 32 kilobit per second links, so over modem, over telephone lines. So many of you probably have never seen what an acoustic modem is. At the very first computers, they used telephone lines. On the telephone lines, what could you transmit at this time? Audio signals with bad quality. So the modem was simply something that a physical device that would produce audible sounds that were put into the lines, and the result was something like 32 kilobit per second. And then it collapsed down to 40 bits per second, which was one of the documented experiences, but there were many more over longer distance. In the middle of the '80s, TCP had this problem. TCP and IP had this problem of congestion collapse. So let's understand where it comes from, and that will explain why we need to do a number of things in the internet today. Here is a toy example, but it's not showing congestion collapse, but simply inefficiency. Here I have two sources, S1, S2, that want to send to two destinations, D1 and D2. And here are the link capacities. In the middle, there are two routers, and the link capacities are 100, 1000, 110, 110. The numbers are very different. Of course, in reality, you don't find such variability, but you could think of it as the usable capacity due to the remaining traffic. Here, there's not much traffic, so there's a lot available, and here it's the opposite. Assume that we have greedy sources. That means sources that send as much as they want. In the internet, it was not as much as they want, but it was as much as flow control was allowing. Flow control, remember, is the thing that a TCP receiver gives, is the size of the window that is sent by a TCP receiver to the TCP source. So if the servers are not busy, but if the network is the bottleneck here, the flow control will allow the sources to send at very large amounts. So here, S1 is sending at 100 kilobit per second, cannot send more because the physical link does not allow more. And S2 is sending at 1000 kilobit per second. What will happen? Well, in the first router, we have to merge all this traffic, and the output is only 110. The numbers have been crafted to be round, so that's exactly 10% of the input. So we have an output that can serve only 10% of the input here. Therefore, there will be losses, dramatic losses here. Right. Assume the losses are proportional. That means here we lose, as a very coarse approximation, we lose 90% of everything that comes in, right? Because we can pump out only 10%. That's optimistic. So in some cases, it's even worse. Because that's assuming we can be as efficient as possible. Here, there is no problem, because here we have demultiplexing. We have the 110 kilobit per second that is moved into 110. So of course, the 110 cannot flow here, but whatever fraction, if this is less than 100 going here, it will flow without loss. Here, in contrast, whatever is trying to go here is limited to 10 kilobit per second. So if there is more trying to go, then there will be losses here. So assume we do this. What will be the rate from S1 to D1, right? So we do this game. S1 and S1 send as much as they want. When the output cannot serve all the traffic, it will drop in proportion to what it can do. What will happen in the sense of what will S1 achieve? Pose the poll in a few seconds. And the majority says A, which is the correct answer. Let's analyze the solution. So at this point here, we drop 90%. That means there is 10 kilobit per second of the first flow that gets here, and 100 here. And now at the second output, we have 10 that's trying to go out over 100, so it's unchanged, 10. So that gives the answer to my first question. The rate of S1 to D1 is 10. The interesting thing is what happens to the other source here. For source 2, we see that the rate of S2 is also 10. First, it gets 100 to go through, but in the second node, it can only send 10, so we send only 10. So take-home message, in this configuration, the total that is sent by each source is 10, so the total throughput of this network is 20 kilobit per second here. So we have inefficiency here, so we have the result here, but we see that this is because everybody was greedy and nobody is managing the network. There is no point for S2 to send more than 10, because at the end, S2 is limited to 10 here. So why is there a problem? It was because S2 was sending too much. But of course, S2 has no way to know that it's sending too much. It has a connection at 1,000. So it doesn't know that later there will be a problem. So that's exactly the mechanism that causes inefficiencies and congestion collapse. We inject into the network here traffic that will not survive. This traffic will not find its way to the destination because there is a bottleneck downstream. But this traffic will cause problem to the rest of the network here. It will cause competition with the other flow that will kill some of the traffic here. If we would know the complete picture, for example, if we had an OSPF view of the network and we would manage the rates, not just the routes, but also the rates, we would say, oh, but S1 you should send at 100 and S2 at 10 here, because 100 and 10, that works, and that would be much more efficient here. So that's a first problem called inefficiency. And that's very easy to reproduce. In lab 5, you will reproduce in the lab exactly this. You do UDP sources that send traffic as much as they want, and you will see that the network is producing an extremely minimal capacity and minimal throughput. But that was an easy example where the network had what is called no cyclic dependency. What is a cyclic dependency? Well, the dependency is when a flow influences another flow. And if we put the graph of those dependencies, here there is no loop. But you can easily create other networks where there would be loops if there are loops in the topology itself. Here is the example I'm using. Here I'm considering a ring, and assume that at every node of the ring, there is a source that sends 2 hops away, right, in the direct direction of the ring here. And this is a completely homogeneous and symmetric system. At every node, there is one such source that sends 2 hops away. All sources are sending at the same rate lambda, and I'm wondering what is the maximum value of lambda that can happen. Assume all the links have a capacity C here. We see that every flow uses every link twice. So on this link here, there is some traffic coming from source I, but also traffic coming from the previous source here. So we see that certainly if the lambda is less than C over 2, then the traffic that goes on the link is less than C, because there's two times lambda in the best case. So there is no problem, there is no congestion, and all the network is transparent, quasi-transparent. Of course, there can be small delays, but there's no reason to have packet losses here. So everything that comes in goes out here. So if I call lambda second the throughput, that is how much of the source I eventually makes it to the destination. We've seen in the previous example, it's not necessarily 100% because of losses here. So I call it lambda second. We see that if we are below capacity of the links, lambda second is equal to lambda. What happens if we go above? Well, we can do a bit of easy computation, we can say what happens in a node here. In the node, there is traffic coming fresh from the outside. That's at the rate lambda. That's an input value. And there's also transit traffic from the previous hop that's trying to go to its second hop. Let me call lambda prime the value of that traffic. So lambda prime is the amount of traffic that survives at the next hop. Then if we're above capacity, there will be a loss. So we do the same calculation as before. What is the proportion of traffic that is accepted? What is the capacity divided by what is offered, lambda plus lambda prime? Therefore, we can see that lambda prime is equal to this ratio equal to what is offered lambda, which, by the way, gives us a fixed point equation that allows us to compute lambda prime. Once we have computed lambda prime, we can also compute what goes to the next hop. Similarly, what goes to the next hop is the ratio of accepted traffic multiplied by what has survived at the first hop. So we can solve this. That's not very difficult. That's a quadratic equation. We have a closed form solution. And here is the result we obtain. And if I plot it here, that's the value we obtain. We see that when we're below capacity, that's the formula we had before, lambda second is equal to lambda when we're below capacity. When we're above capacity, we see that it is decreasing. The more we put into the network, the less comes out. In fact, if we go to the limit, we can easily compute the limit when lambda goes to infinity. We see that lambda second at first order is in 1 over lambda. It means it goes to 0 when lambda goes to infinity. In other words, in such a simple ring network, if the sources can send as much as they want, the more they send, the worse it will be. And in the limit, the network becomes completely useless and inefficient. This is called congestion collapse. This network goes into congestion collapse when we are above capacity. Ideally, what we would like to have is not congestion collapse, but we would like to have a mechanism such that when we reach the capacity, we stay at capacity. Of course, we cannot produce more than what is in place. This network cannot produce more, cannot carry more than C packets per link. So it has a capacity. But what we would like is that when we are at capacity, we serve at least for the capacity of the network. So the first thing to remember is there's a distinction between congestion. Congestion means there's a large queue because this food truck cannot serve more than 2 people per minute, okay? But congestion collapse is when there is a large queue, the food truck becomes in such a chaos that they serve nobody. That's congestion collapse here, which is paradoxical, but it happens in quasi any complex system that we operate. And here we have an explanation for where it comes from. We see that if lambda is very large, we admit into the network a large number of packets that will compete with other packets at the next hops. So those packets that go through a first hop, a large fraction of them will be killed in the network in the second hop. But by being killed, because if this network node is fair, that will cause also other packets to be killed here. So we admit into the network, into the first hop, a large fraction of packets that consume the bandwidth of the first hop, but will never be delivered to destination. So we give resources to units of work that do not complete. If you use this pattern, that explains congestion collapse, and now it can explain it in anything you do. If we receive many emails, we start reading the subject of the email, and then we discover we don't need it, so we don't respond to it. But by doing that, we're spending a lot of time on reading things, emails that we will not handle. So we're using our capacity, our brain, our attention time for things that we will not do. So we can go into congestion collapse when we're submitted to too many things. Web servers, the very first web servers also went into congestion collapse for similar reasons. If a web server, when it receives a connection request, it receives a TCP SYN packet. It's busy creating the socket, replying with a SYN ACK, computing all the stuff, probably also starting some data structure depending on the logic of the web server. And if it is heavily loaded, then it will become very slow to the point that all this work will not complete simply because the people who are connecting to the web server, they see no reply. So they give up, right? You connect to somewhere, you don't see anything coming, you think it doesn't work, you try something else. So you have generated a lot of work on the server that is not used for any useful transaction. So all the modern web servers, Apache and others, have a solution for that, which is called the gatekeeper. They make sure that they allocate only a small fraction of their resources to handle new connection requests, incoming connection requests. Right? Executives have a secretary for that. Executives don't read their emails themselves. They have somebody to filter that, and you disturb the executive only when there's an important email that comes here. So that's the same thing for servers. Let's discover how this is handled in the internet. In the internet, it's more complicated. You can imagine that in a data server, you can do that. You can put at the front end of the data server a gatekeeper that analyzes all the traffic that comes and decides whether or not to really handle it. But in the internet, how do we make sure that all those flows here don't send too much, don't send more than what the network can accept? In order to understand the problem, we need to discuss another topic, which is efficiency versus fairness. We have seen that if we don't do anything in the network, like the internet was in the 80s, it's inefficient, and in the worst case, the network could fall into congestion collapse. So we need to do something for efficiency here. But what should we do? Here is a small toy example where I have a network where I have red, blue, and green flows. I have 9 green flows, 1 red, 1 blue, and different capacities are going here. What is the maximum total throughput of this network? So if we want to reach the total throughput, what can we achieve here? So the total throughput is the sum of the rates of all the sources, right? X0, X1 plus X2, the valuable rate, the value of the rate that is delivered to the destination. Let me close the poll. The majority says, the majority is changing their mind. Okay, the majority says B. Let's see. Well, it's more tricky, admittedly. So the total throughput is X0 plus X1 plus 9X2, where I call X the value that will be admissible, that will be possible to carry, so without losses. So we want to maximize this. Now, what are the constraints? Well, we have 2 links, so we have 2 constraints. I assume here a very simple modeling where I don't model the queuing. So I'm just saying the total admitted traffic should be less than or equal to the capacity of the link. In reality, we can never load a link at 100%, but let's ignore this detail. So that gives those 2 constraints, X0 plus X1 less than 10, X0 plus 9X2 less than 10. So that's a linear program. So you can use MATLAB linear program to solve this. Or you can also look by inspection, and you find that the throughput must be less than 20, obviously, because 10 plus 10 is 20. We cannot do more than the physical capacity. And you can see that if we try X1 equal 10, we give 10 to this guy here, and we divide the rest of the green here into the rest, sorry, X1, yes, X1 equal 10, and X2 also we give 10 to those guys, then we reach 20 megabit per second. So the answer is the total throughput is 20 megabit per second. But how did I reach the total throughput? by shutting down the red flow. If I want to maximize this, I shut down the red flow. It's exactly what happens when there is a shortage of resources. That's what we see in the current economy, where there's not enough resources to produce potatoes or milk or oil or whatever. Then the companies start to do exactly this. You want to buy something, they say, no, we don't sell to you because you're a red customer, right? You cost too many resources for us here. That is what happens if we want to maximize efficiency in a system where there are limited resources. We are grossly unfair. Well, I skipped this question because I gave the answer, right? The value of x0 when we reach the maximum throughput is 0 here. Right? In fact, for whatever solution we have here, we will obtain 0 for this guy here. So we have a problem. We cannot simply say in a network, in order to avoid these efficiencies that are caused by greedy sources, we want a system that will try to maximize the total network throughput, because doing that cannot be a socially admissible scenario. You cannot simply, Swisscom cannot say, oh, you are 2 hops away from destination. Doesn't work for you. We're sorry. Come back later when there is less traffic. But the first notion to compare us against in this context is what exactly efficiency means. What you would like in a network is not to maximize the total throughput, but to be what is called Pareto efficient, which, as we will see, still gives us a lot of freedom. Pareto efficiency is a term that some of you probably know from other courses. It's a concept that comes from economy, but it comes also from, in networking, it's also used a lot. Essentially, an allocation is, or in general, an allocation of resources is Pareto efficient if we cannot improve it at the expense of decreasing somebody. So an allocation here is the value of the x here. My vector x is Pareto efficient if I cannot find another allocation that will unilaterally, for any other allocation, if I unilaterally increase one of the resources, I must decrease one of the others. Here. So if we're not Pareto efficient, that means you can increase unilaterally one of the resources. So if you're not Pareto efficient, you're stupid. Why should you give 1 to you, 2 to me, and when it's possible to give 2 to you and 2 to me? Right? So something that is not Pareto efficient means something that can be obviously increased. Something that is Pareto efficient means if I try to increase one guy, I must automatically decrease another one here. For example, is this allocation here that we have discussed before, is it Pareto efficient here? Well, one way to reason about Pareto efficiency is to see whether there are binding constraints, which in networking are called bottlenecks here. If I look at link 1 here, then it's a bottleneck for sources 0 and 1 in the sense that I cannot increase 0 or 1 because of the constraint here. So I cannot increase 0, I cannot increase 1. And similarly, for the green flows, it's a bottleneck here. So I cannot increase any of the sources. So it's obviously Pareto efficient. None of the sources can be increased unilaterally. So that's Pareto efficient. Hopefully, it's not the only one here. So here is a slightly different example. Here, I have 1, 2, 3 links. I have 4 flows. And here are 3 possible allocations here. Which allocation is Pareto efficient? Oops, no, that's right. Due to time, I make it a bit shorter, so I close the poll in a few seconds. Closing. And the correct answer is F, both B and C. To see why, we can see first that A is not Pareto efficient, because if I look at those values here, 1 and 0.5, obviously I can increase the blue one, doesn't change anything for the rest, so it's not Pareto efficient. The others are. So this one, for example, we see that all the capacities are reached everywhere. So our allocation B is Pareto efficient, and allocation C also is Pareto efficient. So we have two Pareto efficient allocations, which leaves us to the question, which one should we use if we want to design an internet protocol that avoids congestion collapse by allocating rates to sources, for example? If we would use SDN to give the rates to the sources, which should we use? Should we use C or should we use B? Certainly we should not use A. This is not efficient. Certainly we should do something, because if we let the rates be whatever they want to be without any control, we can be inefficient and have congestion collapse. But what should we do? It's a dramatic question. The answer to which we will see next week. Voilà, thank you.